Alright, so for this video, I'm going to talk about the next step in the ray tracing process, which is we already constructed the array for each of our pixels, and now we're going to test the array with the geometry that we have in the scene, right? If we generalize the process of ray tracing, discounting the physical phenomena that we're really trying to mirror here, there's 4 steps for ray tracing. One is cast the ray. Already done that. Second step is intersect. Third step is shade. Fourth step is, there's really no fourth step, but right color to pixel. This could be generalized to the ray tracing, direct ray tracing. What it means to be direct is that we do not try to simulate the process of light bouncing, in other words, global illumination. So we only care about the direct lighting. So direct ray tracing, cast a ray, intersect with some geometry, and based on the intersection result, we shade the point. Then we write the color of the point to the pixel, which is what the viewer would see. We covered cast ray already, right? Covered this, and this video is we're gonna cover intersection. And something I think I want to mention is that for any ray tracer, the intersection routine is going to be the most important for performance. Ray tracing is really slow because you literally sometimes have to test intersections between the ray and millions or billions of triangles out in the scene. So what people typically do for large scenes, they use some binary space partitioning, acceleration structure, and the intersection routine will just be reduced to as few polygons as possible. And then there's specific ways you can do intersection that's faster than what you would the naive solutions. Here we're just going to present, since on shaded toy we cannot store any explicit geometry, we're going to use procedural geometry as an example, which I'll explain later what it is. So the intersection routine, very important. This is what makes a ray tracer. So why don't we begin? What I'm about to present will be the analytical solution to doing ray tracing. What it means is that we would use some kind of equation. We list some kind of equation, some relationship of some properties of variables with t, which is a reminder for the parametric form of the ray. T is the distance of the ray that's traveled to the intersection point. So that's distance from the intersection point to the ray origin. Assigned distance, really, because if t is negative, then you're on the other side of the ray. So you have some kind of equation. This is an equal sign. Just try to make it thicker. And we reduce this down by isolating t on just one side and some giant mess of expression on the other side with all the other known variables, so that we can test intersection with the snap of a finger, right? Just one single computation and we get t. Obviously, in contrast, the opposite solution is iterative approach. You kind of do it iteratively, which I think is a lot more elegant than what the analytical solution is, because obviously for a different solution you will have a different analytical solution. But for iterative approach, you can kind of do it uniformly for all the geometries, and there's some rules to it, which I will show also, but not in this video. So to keep everything simple, I'll limit the 3D primitives that would be intersecting to just be a 2D plane, well, 3D plane, 2D plane in a 3D space, and a 3D sphere. 2D plane extends infinitely outwards in its own dimension and has a width of 0 in the dimension that's orthogonal to the plane. And the sphere takes a position in 3D with all the points on the surface with the distance of r away from the center. So The surface of the sphere is formed by all the points in 3D space that has a distance of r away from the center. The plane is formed by having all points in the 3D space that is orthogonal to the vector. So, if you sample some points on a 2D plane and you draw it from the origin of the plane out, these vectors, the dot product of these vectors with the normal of the plane is always going to be 0 since they're orthogonal. Surprisingly, ray intersection for spheres is way more involved than it is with the plane. So why don't we start with the plane first? To simplify matter even further, we can assume the plane's origin is going to be at the center of this plane is going to be at the origin. And another defining characteristic of a plane is its direction. So why don't we set the direction to y? So it's really the ground plane. So taking place at the 0 xz plane where the y is equal to 0, and surface is gonna point up. So if you look down from the camera, we're gonna see the plane. That's like the ground. Let's try to be more generalized in this case though. Let's just put n here for any. This could be used for any plane. However, we don't have to be generalized with the origin of the plane. As we'll see later, in my opinion, a way more superior way is to have a fixed equation of geometry that will take place in the origin, then transform the space in which the geometry resides. That way, we'll have an inverse transformation done to the geometry in the scene, by just simply transforming the space. You will see how that's done later, but not in this video. All I'm letting you know is that it's good enough just to assume the plane will overlap with the origin. That will be good enough. So again, to explicitly write out the property of the plane, for all points that overlap with the plane, say P, there's some random points in the plane, the dot product with the normal is equal to 0. Now recall that what a dot product means. Say A and B are some arbitrary vectors. The dot product of them will be the magnitude of A and B multiplied with the cosine of theta, which theta is the angle in between A and B. And if A and B are orthogonal, meaning they make a right triangle, they have a triangle, not a right triangle, but a right angle. An angle of 90 degrees, that means this portion, cosine of 90 degrees, will turn to 0. And no matter what magnitudes they are, this expression will always, degenerate into a 0. So this is the convenience of dot product. If a point is inside a 3D plane, a dot product of the point with the normal of the plane will also be 0 because the vector out from the origin of the plane will make an orthogonal vector with the normal of the plane, and we assume the origin of the plane is at the literal origin. Okay. Now let's bring up our parametric form of the ray that we have. Well, this is ray direction and this is ray origin. Now you can think of T as some kind of slider. You can put a point that represents whatever the parametric equation is representing right now on there. Like T is just going to be the distance from a point on the ray to the ray origin. So this is T. You can drag this thing along. You can drag it wherever you want except backwards, right? Because T is constrained in the range of 0 to infinity. So if the ray intersects with some kind of geometry, there's going to be intersection points. We can drag this T, just conceptually, we drag this T right up to the intersection point, where T will represent the distance from the intersection point to ray origin. And we somehow get this T and plug it back to this expression. This expression will be equal to the intersection point in 3D space. However, we don't know what that t is, and that is the definition of unknown variable, right? What we can do is to make an equation out of it. We can just assume that t is the unknown variable that will make the expression, this expression, intersection point of the intersection point. And therefore, we can plug this expression as p in our plane equation. And now this forms an equation that we can actually analytically solve. So let's just go ahead and do that. Right origin plus t times right direction. We assume that t is already the unknown distance that we're seeking. So this expression has become the 30 point. Now the 30 point dot product with the n equals 0. Now remember, the intersection point with the plane will land somewhere in the plane, and that intersection point will always make a right 90-degree angle with normal. This is why this equation is always true. Now ray origin is a known variable, RD is a known variable, normal is a known variable. T is unknown, but we can easily solve it since we only have one unknown variable in one equation. So we can distribute the dot product. So ray origin dot with n plus t multiplied with ray direction dot with n. At this point is really t ray origin dot product with n over ray direction dot product with n. There it is. That is the analytical solution to ray versus plane intersection. However, there is some caveat you need to watch out for. Now remember, t is only valid if it's in a range of 0 to infinity. However, this expression does not guarantee that to be true. Think about what it means if the t is negative. If t is negative, that means this is our ray. We're testing it to some geometry, but the intersection happens behind the ray. So that actually counts as a miss, right? So that in that case, you can't use t as the distance because it's negative. So that's special case number one. Special case number two is when the denominator becomes 0. That means you're dividing by 0, and you cannot do that either in math or in computer science. Well, what does it actually mean when dot product is equal to 0? Well, that means the ray direction normal or orthogonal, which in turn, if we draw it out in the plane space, that means ray direction must be in its own xz plane that is parallel to the plane, meaning that these two will never intersect in any ways. So that is what it means when a ray is orthogonal to n. So first two cases, you check if the denominator is 0. If the denominator is 0, they do not intersect. If the t is negative, they do not intersect. Only when t is between this range is a valid t, and that indicates that there is actually an intersection occurring between your ray and the plane. Right? That is our first analytical solution to a plane. Now we move on to a more elaborate one. So a 3D sphere. Again, we're going to make the same assumption that the center of the sphere will be at the origin. And the sphere's surface is made up of 3D points that have a distance r away from it, meaning that the radius of the sphere is going to be r, right? That is the definition of a sphere. So any point P on the surface of the sphere, the length of P is going to be r. So the length of P is going to equal to r. Any point that fits into this equation will, if a point P fits in this equation, that means the P is part of the surface of the sphere. But length is kind of, it's not friendly to what we're doing. We can't really expand it out or cancel it out. A more, linear algebra friendly way of writing the same thing is dot product the P with itself. That will give the square of the length of the vector, which is the square of the length of P. What we really want is the length of P, so we do a square root to cancel out the square term, which is equal to R. But again, when you're programming, you should know that square root terms are kind of expensive to do, even though that's starting to change due to the special processors. However, we can just do a simplification. It doesn't hurt. It's nice to have a square than a square root because square root has nasty properties and it's easier to draw a square anyways. So if a point fits in this equation, that means the point is on a sphere. Again, we can plug the parametric form of the ray equation into as P, assuming that T value is the unknown variable that we're solving for, which is the intersection distance from the ray origin. So exact same strategy as last time. The equation is going to be a bit long, so I'm clearing out the page in anticipation. So keep in mind, R is the radius of the sphere, and all P on the surface of the sphere has this property. All right, so we plug it in. We plug in the sphere's equation. Equal to R squared. Now, R0 is known, RD is known, right? And R squared is also known because we need that to be defined for the sphere. We know how big the sphere is before we intersect with it. Now, again, the only unknown variable becomes T, and this equation becomes solvable. All right. So let's expand it out by distributing the dot product. Did I just change my notation? Hold on. These R's are supposed to be lowercase. Sorry about that. I have no idea how to make the eraser bigger on Sketchbook. So maybe I have to get the paid version to do it. I don't know. So ray origin, expand it out, dot product ray origin plus 2 times T ray origin dot with ray direction, right? And lastly, plus T squared multiplied with ray direction dot with ray direction itself equals R squared, and yikes, we have a square here. What do you do when the equation has a square? Well, you turn it into a quadratic equation. And if it becomes a quadratic equation, we can just use the quadratic formula, right? Told you, the sphere is going to be harder than the plane. All right, just making sure everything is correct. Yep. And again, the quadratic formula for a quadratic equation is x equal to negative b plus minus the square root of b squared minus 4ac over 2a, where b is the coefficient for the degrees of 2, and a is the coefficient for degrees of 2, and b is the coefficient for degrees of 1, and c is the coefficient for degrees of 0. So we can write t out using this quadratic formula. So negative 2 r ray origin dot ray direction plus minus square root of ray origin dot with ray direction square. minus 4 AC. So it's just God. I'm just gonna rewrite that. Alright. Over 2A. So it'll be. And this is, let me just double check everything. This is the equation. Yep. This is the equation for, the analytical intersection test between an array and a sphere. It's quite elaborate, but it's gonna be, it's O of 1 in almost anything, because just do a single computation, you get the intersection point. Let me just drink some water. That one was a big one. Again, just like with the plane intersection, we also have some caveats of this equation. First of all, you have to watch out for the square root term. The stuff in the square root term better always be positive, because you can't have complex numbers in here. And the whole expression better be positive or 0. If it's negative, then that means you miss the intersection. And again, unlike the plane intersection test, it is impossible for the sphere intersection equation to have a 0 denominator, because it's literally the right direction dot with the right direction, which is always going to result to 1. So the denominator is constantly 2. You can't even optimize this out just to be a 2 or something. It's up to you, but this is the complete mathematical equation for ray versus sphere testing. So there's obviously redundant terms that you can extract out. You can just preemptively calculate these terms to avoid recomputation of the same values. And that's details of the implementation, so I will not talk about them here. Alright, let me just double check if everything is correct. I can mention all the stuff that I want to mention. Right, I think that'll be it. So since there's so much theory, I'm not going to do any implementations. I'll leave that for next video, and just for fun, why don't you try to derive the intersection test, the intersection equation for a 3D cube. A 3D perfect cube with, each side of width. How do you compute t in this case if the object is a perfect cube with dimension of w that resides with its center and origin? What do you do in this case? It's always fun to do these derivations, I think. So I'll leave that as an exercise. Do not look it up. Try to solve it yourself. It shouldn't be too hard. So, okay, I'll see you next time.